All right, so this video is covering rationalizing the denominator. And just to review a topic we covered when we first started talking about radical expressions, was what makes a radical expression simplified. Well, we've covered the first one, no perfect squares. We've covered that at length. And when you talk about division, that takes care of this second one, no fractions in the radicand. But what we're really focusing on in this case is, and we talked about this in class, or if we haven't, we will discuss it, but why can't we have radicals in the denominator? That's the purpose of the rationalizing here. So the idea behind the rationalizing is that this idea of multiplying a quantity by 1 doesn't change its value. So no matter what, if I'm multiplying by about 1, I'm keeping that value the exact same. So to get rid of that radical in the denominator, that's what we're thinking about doing, is we're multiplying by a value of 1. So to get rid of that radical, we're going to multiply both our numerator and denominator in a value that will cause all the radicands, in the denominator, all denominator radicands to contain perfect square values. So in other words, we're getting rid of any radicals in a denominator. So I'm going to show you an example to see this process. And so we have square root of 5 in the denominator, and what we really want to focus on is what radical is causing us problems. It's the radical in the denominator. So if I can multiply this, so I want to say, how could I get rid of this radical? Well, if I had a perfect square in the denominator, so now I have square root of 25, I could get rid of that radical in the denominator, because now I would just have this fraction over 5. So to be able to do that, though, I have to look at what I'm multiplying by. I can only multiply by a quantity of 1. I want to multiply by 1 here so that I'm not actually changing any values, I'm just simplifying. So if I multiply by root 5 divided by root 5 is 1. If I multiply by root 5 in the numerator and denominator, I haven't really changed any values. So if I multiply these, 3 root 2 times root 5 would be root 10. So I would have 3 root 10 in the numerator and 5 in the denominator. So now this is a completely simplified rational expression because the denominator no longer contains that radical. So here's your you-do. So pause and try this one on your own. So again, which radical is causing us the problems is the one in the denominator. So if I multiply by root 3 in the numerator and root 3 in the denominator, I know I said those backwards, but if I multiply here, I have root 9 in the denominator, which would be just 3. In the numerator, I have 4, and then both of these are under roots, so I multiply them together, 15. And then 4 root 15 can't be simplified anymore, so there is my answer. So the basic idea of rationalizing your denominator. Now, of course, there's expansions on this. And sometimes in that process, when we're simplifying, when we're rationalizing, we're going to need to simplify our expression further after we do the rationalizing. So in this case, if I do this one and I'm rationalizing, I need a root 2 on numerator and denominator so that the denominator becomes root 4, which is 2. When I multiply in the numerator, 4 root 22 now, and 4 root 22 comes along here. I have now, so the thing I want you to notice is, I have a number outside of a radical and a number outside of a radical. I need to simplify those if possible. So just like any fraction, 4 over 2 would be 2, and then root 22. The denominator would be 1. You don't really need to put that. It would be extra, not really necessary. But if it were a fraction that's still simplified into a fraction, I would have a numerator and denominator still. But the idea that if it's in radicals, if numbers are in radicals, you can simplify them. But if their numbers are outside of radicals, you could also simplify them. So here's one for you to try. So pause and try this one. So first, radical 10 over radical 10. So I'm multiplying by 1. The numerator becomes 5 root 30. the denominator becomes root 100. So 5 root 30 in the numerator, 10 in the denominator, and then again, outside of the radical, 5 and 10 can simplify. 5/10 is 1/2, so that would be root 30 in the numerator and 2 in the denominator. So root 30, because it's in the radical, can't be simplified with the 2, but if they were both in radicals or both out of radicals, you certainly could. All right, so then the other kind of idea here when it comes to rationalizing the denominator is that you want to realize that the best choice for multiplying may not always be by using the radical that's just sitting in the denominator. So if I were looking at this setup here, and what you really want to look at when you're looking at the denominator is what's actually causing you the problem. Is it the 3? Well, no, 3 is allowed to be in the denominator. That's fine. It's the radical here. And there are a couple of ways to deal with this radical. But what I suggest doing, and again, there's multiple ways. You could multiply by root 20 if you really wanted to. But what I suggest doing is simplifying first. So I'm going to take this denominator of square root of 20, and I'm going to simplify it. And I found a perfect square here, square root of 4, which I can take, and square root of 5, which I can't. So I'm just going to simplify this out now. So 7, and this is 3 times 2 root 5, 7 over 6 root 5. Now the idea is here, when I'm going to simplify, now I have root 5 instead of root 20. When I'm looking at root 20 here, there are perfect squares inside of it, so I don't need to multiply both numerator and denominator by 20. What I need to multiply by is the part that's actually not a perfect square, which is the 5. So if I multiply by root 5 in the numerator and denominator, and I get 60 times square root of 25, or sorry, 6 times square root of 25, 7 root 5 over 6 times 5, 7 root 5 over 30. The idea is you're dealing with smaller numbers if you try to simplify your radical first. There is an alternate way to do this, and so I will just mention it here, and you can do whichever way you prefer. And that way is to think about how can I turn this 20 into the smallest perfect square possible. Instead of multiplying by root 20 top and bottom, which again, you could do that, you just have more simplifying to do at the end, a lot more simplifying to do at the end. But if I can think about this is, how can I turn this into a perfect square? Well, root 20 could be turned into square root of 100, like I'm doing here. I mean, you could do it this way and just, it's an alternate way if you feel really good about your perfect squares. It's not always going to be the easiest, but it is a secondary method you could use. I like to personally simplify first, so that'll make it a little bit easier to see what is actually the problem in the denominator. So it's definitely your choice on which one you do, but you'll see that when I'm doing my answers, I'm going to simplify first. So I always look to simplify the radical to start the problem out. So here's one for you to try. So pause it and remember thinking about using square root of 27 may not always be the best option. So if I simplify this, 27 is 9 and 3, and square root of 9 means that I really have 18 over 5 times 3 root 3. So I had the square root of 9, I already had a 5 outside, so that denominator becomes 15 root 3. So the problem is the root 3 here. So I need to multiply both numerator and denominator by root 3. So numerator becomes 18 root 3, and the denominator becomes 15 root 9. So 18 root 3 over 15 times 3 is 18 root 3 over 45. And the last thing, I want to make sure this 18 and this 45 have a common factor. I can divide both of those by 3. So that's, actually, I can divide those by more than 3. I can actually divide both of those by 9. So simplifying that fraction becomes 2 root 3 over 5. So not multiplying by root 27 certainly saved me some higher level multiplication that I didn't want to necessarily do. All right, the last kind of rationalizing to touch on here is that some denominators, and you'll see a couple of these for practice, just to get some experience. So you may need to write this down and really think about this. But when you have a denominator that contains a binomial, you need a special method to rationalize. Because if I say, oh, okay, here's root 3, it's causing me the problem, so I'm going to multiply by root 3 in the denominator. If I do 2 minus root 3 times, and so I need to multiply the whole thing by root 3, I can't just multiply a small piece of that denominator. I have to multiply the whole denominator by root 3 when I've written this. So what do I end up with? I end up with 2 root 3 minus square root of 9, so 2 root 3 minus 3. I got rid of the radical in the second position here, but I added a radical in the first position of the denominator. So multiplying just by a simple radical isn't going to take care of the getting rid of roots. We still have that problem. So the kind of radical we need to multiply by is called a conjugate. So the conjugate of a binomial, and so you'll see this written, the conjugate of a minus b is a plus b. It's also the opposite. For a plus b, the conjugate is a minus b. So it's kind of like this pairing. And so the idea here is, and we can go into more detail with this and ask some questions about it, but the idea behind this is that these two pairs, if we use the conjugate, so if I have 2 minus root 3, its conjugate is saying, okay, keep the same values, a and b, 2 and root 3, but I'm going to do addition instead. So I'm going to multiply by the conjugate, and you'll see what happens here in a second. If I multiply both the numerator and denominator by the conjugate, and I like to use the parentheses to make sure I'm remembering to distribute where necessary. If I multiply 5 in the numerator, so that's 10 plus 5 root 3. In the denominator, though, I need to FOIL. So that's 4 plus 2 root 3 minus 2 root 3. And you might already start seeing what happens, minus square root of 9. If I look at the denominator now, I have a positive 2 root 3 and a negative 2 root 3. Those cancel out. My numerator stays the same. In my denominator, I have 4, and this is minus square root of 9 is 3. 4 minus 3 is 1. So my answer is 10 plus 5 root 3. So what multiplying by the conjugate does, and in this case it canceled out to be 1, but multiplying by the conjugate in general, what it does is cancels out your radical. So here is a problem where we had a binomial. The method to change it is to use the conjugate. So here's one for you to try. So think about what the conjugate actually is and then use it to multiply. So the conjugate would be, and make sure you paused and tried this on your own. If I group this, it's the same components, but it's a subtraction. So I need to do 4 minus root 2 in the numerator, 4 minus root 2 in the denominator. In the numerator, I'm just multiplying, or sorry, distributing. So I have 4 root 3 minus root 6. In the denominator, now I'm FOILing. I have 16 minus 4 root 2 plus 4 root 2 and minus root 4. I hope that doing this method does remind you of something when we were FOILing with polynomials before. In the denominator now I have these two cancel out. I have 16 minus 2, so that would be 14. And that is as simplified as we get. So rationalizing different denominators, binomials are the trickiest ones, but if you remember that idea of conjugate, and you're going to use that conjugate sum to practice.